to the camera.
The purpose of the experiment is to study the behavior of photons as they travel from one end of the tube to the other. To begin with, the individual photons are sent through just one of the slits.
Each of these dots arriving represents a single photon. So most of them are coming along this point. Some of them lie above or below that point, but the distribution is nice and smooth.
Now the second slit is opened up, and the experiment repeated. Each single photon must still pass through one of the two slits, so the results should still be the same.
Classical logic would say that what we would get when we open both slits is just the sum of these two detection patterns.
But what we actually find is this: an interference pattern. Something that should be impossible.
What that implies is that the single photon is somehow going through both slits at the same time. It's not making a choice as to go through one or the other, but is going through both simultaneously.
In other words, each photon exists not just in two places, but also in two times.
So we have this very strange notion that this single photon can be in two different places at once. It could be delocalized. But we can think also of a single photon being in two different times. So both space and time have become delocalized and fragmented.
On the surface, we feel time is ordered, but that belies a different reality. We are totally unaware of the chaos and unpredictability that lies deep within the atom. Not surprisingly, our understanding of time comes from our everyday experience. And it's for this reason that we cling to yet another of our assumptions about time, that it never stands still. In fact, one thing that sets us apart as humans is the knowledge that time waits for no man. That time doesn't merely exist, but is constantly flowing. But one discovery proved that this isn't always the case.
Dr. Tom Bolton of the University of Toronto made more than 40 observations of Cygnus X1.
In 1971, astronomer Tom Bolton embarked on a project to observe a mysterious X-ray source called Cygnus X1, an object assumed to be a distant neutron star.
I started to look at Cygnus X1 because I thought it would be a good opportunity to determine the mass of a neutron star. And nobody had done that yet.
Cygnus X1, some 8,000 light-years away, is one half of what's called a binary system.
The binary system is a pair of stars that are gravitationally bound to each other, just like the Earth is bound to the Sun, and they orbit about their mutual center of mass.
By measuring the speed and orbit of X1's binary partner, Tom was able to work out the mass of his neutron star. But the figure he arrived at was far, far bigger than the one he'd been expecting.
That turned out to be about 10 solar masses, with a significant error, but still way too big to be a neutron star. So I had to start thinking about what are the alternatives if it's not a neutron star.
There was only one possibility that fitted the data, but it was something that few people believed actually existed.
As far as I knew, the only object that would fit that description and produce X-rays was a black hole. So I said so.
Tom's discovery caused a sensation. The first incontrovertible proof that, far from being a figment of people's imagination, Black holes were in fact very real indeed. Since their discovery 25 years ago, we now know that the universe is teeming with them. But it's how black holes affect time that make them so unusual. Black holes are so massive that their gravitational pull approaches infinity. And according to Einstein's second theory, that of general relativity, very intense gravity slows time in a similar way to moving at very high speed. So if you were to watch someone fall into a black hole, you'd notice that their time was beginning to slow down. So much so that at the very center, where the gravitational pull is infinite, time would stop altogether. Time would cease to exist. That there are places where time can come to a grinding halt seems frankly incredible. But that's only because we live in such a uniform corner of the galaxy. Warmed by a benevolent sun, far from any extremes of gravity. Beyond our everyday environment, time is very different. Not only is it irregular, it's also chaotic. It can even stand still. But for all its vagaries, there's one thing that time never seems to do, and that's turn back on itself. Although time may be hard to define, there's one truth that has always been beyond doubt, and that is time only has one direction, and that is forwards. Which, when you think about it, is a little odd. After all, my physical environment offers me enormous freedom. In my three-dimensional world, I can go any place I choose. But with time, my freedom to move about is confined to one direction. Of course, in our imagination, it's a completely different story. In 1895, a short novel by a former schoolteacher named H.G. Wells brought to life one of humanity's oldest dreams.
So I travelled, stopping ever and again, in great strides of 1,000 years or more, drawn on by the mystery of the Earth's fate, watching with a strange fascination the sun grow larger and duller in the westward sky, and the life of the old Earth ebb away.
In the earlier part of the 19th century, there were stories that involved time travel or kind of visions of often the future. But what tended to be different was these were often kind of explained in terms of sort of either dreams or supernatural occurrences or visions or something like that.
Wells' story, called The Time Machine, took the idea of time travel and made it seem scientifically viable.
I'm afraid I cannot convey the peculiar sensations of time travelling. They are excessively unpleasant. There's a feeling exactly like that one has upon a switchback, of a helpless, headlong motion.
When he's describing the physical sensations of time travel, Wells talks about a nightmare sensation and excessively unpleasant and so on. And he, the sort of the staccato sort of flashing by of day and night as being incredibly sort of nauseating and disorienting.